Okay, let us resume the program. I'm happy to announce the second keynote speaker of today. That's Erik Verlinde, and he will talk about string theory, emergent gravity, and the dark universe.
Yeah, thank you very much. It's a pleasure to be here again at the second conference on the information universe. I think that information is an important concept in our present day. I mean, we clearly live in an information age. But just to clarify, what does information mean for me? It doesn't mean that it always has to be useful. I mean, information in physics, we generally, why is this? That's a good question. All right, but anyway, I want to explain that information for me means something we can measure in terms of units, namely bits. And this is the definition already that Edwin mentioned in the beginning. I mean, where we count how much information by counting how many bits we can have. We need to describe it. And this is why information can be thought of as entropy. And certainly in physics, that's the way it plays a role. And so we may ask how much information is contained in the universe. Already the first speaker, Padmanabhan, he talked a lot about indeed information in the universe. In particular, we have, well, according to current theory, we have all of the photons in the universe carry a lot of information. That's an entropy of about 10 to the 90. But if you add all of the black holes and assign them an entropy proportional to their area, you get something like 10 to the 100, maybe 10 to 110. But nothing like what we have in our entire universe, because actually I claim that there's more information. Oh, what's happening now? Someone is...
Somebody's trying to get rid of you in the field.
Okay, good. It's still there, but okay. I'm going to indeed assign more information to the universe. Actually, I'm going to look not only at particles, not only at the photons, but there's more in the universe. In particular, there's dark energy and there's dark matter. And I claim that the dark energy is not something we can think of as really just a constant without any, microscopic degrees of freedom, without any dynamics. It's really something that will drive the universe and actually carries most of the entropy. And so this picture is incomplete in our current laws of physics. Indeed, if you look at our universe from our perspective, we can think about our universe as sort of being contained inside a giant sphere. And I will argue that most of the entropy indeed is contained in dark energy. And the cosmos, when viewed from our perspective, actually fits within one Hubble radius. And so the Hubble radius I think of as the size of the horizon in which, of the universe in which we live. And indeed, the horizon accounts for a certain amount of entropy. It's like 10 to the 123, I think if the correct number is, but of this order. And that's a big number, much larger than the entropy we associate to normal visible objects like the matter and the photons. So most of the entropy is actually carried by the dark stuff, the dark part of our universe. This I want to argue, and I'm going to indeed discuss consequences of it. This all goes back indeed to the ideas about black hole thermodynamics, and we have already heard many talks about this. If I think about a black hole, it has an entropy proportional to its area and also a temperature that we can associate to its surface, to the horizon, which is associated to the surface gravity. And these are formulas due to Bekenstein and Hawking, and they changed really the way we thought about gravity. In particular, they made the laws of gravity, which you can, in certain approximation actually can be recast in this form, in the sense that it follows from Einstein's general relativity that the change of the mass of a black hole is related to its change of its area. But this equation is the same when you make these identifications as the first law of thermodynamics. And so just as was mentioned earlier, I mean, we can try to turn this around and interpret the Einstein's equations therefore as laws of thermodynamics. And this is what the idea of emergent gravity is. It's sort of telling you that gravity must be derivable from a microscopic theory. I immediately want to mention one of the thought experiments that led to these ideas, and that's due to Bekenstein. It's going to play an important role in the rest of the talk, and actually it's a beautiful thought experiment. Namely, without thinking about black holes, or actually saying it this way, we do a thought experiment with black holes, but we're going to learn something about matter that's independent of gravity. And namely, he asked the following question. If I have a black hole and it has a certain temperature, then I can lower a box inside the black hole and ask what is the amount of entropy that can be contained in this box of size r. Well, the force that acts on the box is actually proportional to the surface gravity, and therefore I know how much work I do when I lower the box, and actually how much energy I lose. Actually, it's proportional to the displacement. If it is really a box on the horizon, the displacement of the box is F times r, and that must be equal to the temperature times the change in entropy. And the temperature is proportional to the acceleration. Well, from this equation, you can read off what is the change in entropy. Namely, it's equal to 2 pi m r, and these are just natural units. And so it's proportional to the mass and the size of the box. And this must be the maximum amount of entropy that you can associate to any box of size m, of mass m and size r, independent of g Newton. Because actually g Newton drops out because the entire argument only uses the acceleration at the horizon. And so I'm going to actually see these numbers appearing later in the talk. So what I want to do is give you indeed some brief history of how these ideas were developed. I think Manus Visser will probably say a little bit more about these developments, but I think just to have somewhat of a perspective, I mean, black hole thermodynamics already started in the 70s. It's really, that's why the idea started, with people like Hawking, Bekenstein, and there was an important paper by Hawking, Bardeen, and Carter who formulated the laws of black hole thermodynamics. And then there came a big discussion with people wondering what this entropy law really means. Is it really information that's associated to the black hole? What happens to information that goes in? And this became the information paradox. And eventually, out of these ideas came this proposal of 't Hooft and Susskind of the holographic principle. These are the kind of papers that were written from mid-90s to mid-80s to mid-90s. And then there were two developments sort of that continued. One was trying to think about the implications of the holographic principles, in particular Jacobson and Padmanabhan, who wrote papers, well, from mid-90s till even today. I mean, there's another development actually that came from string theory. And string theory came from a different corner. It tried to understand what quantum gravity was. And surprisingly, they were able to explain in a rather deep way what black hole thermodynamics is. Really have a microscopic understanding of the black hole entropy. And these were discoveries made by Strominger and Waffa, and later worked out, and eventually very quickly led to a concrete realization of this holographic principle, namely the ADS-CFT correspondence. This is discovered by Maldacena also in the mid-90s, but it got developed and actually is still a very active and sort of leading topic in the field of string theory. And really they integrate many of these ideas about black hole thermodynamics, holographic principle, and emergent gravity. And actually it's in that context that I wrote a paper in 2010 on entropic gravity that eventually led me also to think more in a different way about what gravity really means also at cosmological scales. But it should be put in this context. And indeed, from that day, many people started also thinking more about the connections between gravity and information, also in the context of string theory, because there we have a microscopic description, either using strings or what's called D-branes, or using this ADS-CFT correspondence. And the current development is sort of where people try to understand the connection between gravity and quantum entanglement, where many authors have contributed. And then there's these developments having to do with black holes, having to do with also ideas indeed about quantum entanglement and space-time, which I will mention during the talk. Eventually my goal is to go to de Sitter space, because that's the space that's closest to our world. So de Sitter space I think about, well, actually as a universe that's dominated by dark energy. It has a geometry that looks like this. It has a horizon. and it has therefore also an entropy, and that's already what I mentioned. That entropy we can write down in the same way as Bekenstein and Hawking did, as the area of that horizon, and it also has a temperature. And this has a very important consequence, because if it has a temperature and an entropy, I cannot think of this as being a ground state. I mean, it's really an object that has many possible states, an entropy that's very large, and an entropy, a temperature that's very small. And this is going to have observational consequences when we think about gravity. In particular, these ideas about emergent gravity. So I already want to point to you an observational fact that sort of suggests that this is on the right track. Namely, if I look at this universe and I put a tiny galaxy in here, you might wonder, what does it know about the size of the universe, or even the fact that there's a temperature or there's a Hubble constant? Because the universe really expands very slowly at the scale of the galaxy itself. However, when you look at a galaxy and ask what happens to its rotation curve, it deviates from the Newtonian law if you only put in the matter that you see at a scale, actually an acceleration scale, that is determined by the Hubble parameter, by the expansion rate. In particular, you find that the deviation occurs when the Newtonian acceleration drops below this critical value. And this is an indication that galaxies know something about this what I would call the temperature of the underlying degrees of freedom. There's another way of rewriting this relation that also suggests that it has something to do with holography and these laws of thermodynamics. What I'm going to do, I write this relation in terms of an area, which is the area of a sphere of a certain radius r. So in this plot I have the radius this way and the velocity this way, but I can calculate the acceleration, but I can also calculate the area of a sphere. And this is what this area is. So this is the area of a sphere of a certain radius, and this is the entropy you might think about as an entropy, because it's an entropy of a black hole that would be sort of this size. This is the energy contained in that same region, and if I divide this by the temperature of the de Sitter space of a universe with only dark energy and this temperature, this is also an entropy. When this entropy falls below this number, this is when the deviations start occurring. Because this relation and that relation are the same. Just I put in some constants like h bar and c, but they simply drop out and you get back to this relation. But here it reads like a thermodynamic relation with an energy and a temperature and an entropy. And this is where I will indeed explain why this actually has to do with the entropy of our universe and what are then the deviations that will occur. But let me go back to what we know from string theory. I mean, string theorists don't like the Sitter space. They don't like a universe with a positive dark energy. They try to think about exact descriptions and microscopic theory, and can do this best in a universe that has the wrong sign cosmological constant, namely a negative one. This is called anti-de Sitter space, and this is a picture of it. Indeed, this is where you can understand black holes very well. And you can also understand how to describe them microscopically. Actually, the black hole has been disappeared here. There's a black hole in this picture that indicates, actually, in this correspondence that there is a thermal state, because a black hole has a temperature, it has an entropy, and therefore we are in an excited state of the theory. And we can even explain where this entropy and this temperature comes from. It has to do with the fact that the matter that you throw in and that forms the black hole no longer is in the normal state where we can describe in terms of particles. It really goes into a new phase that actually consists of sort of hot gas of strings connecting those particles, which from the boundary actually corresponds to a gauge theory that gets deconfined and gets thermalized, and many degrees of freedom start to enter, because eventually this state will explain all of the entropy of a black hole. It explains all of this entropy. Something that's impossible to do just by thinking about our normal physics in terms of particles that move on space-time. So there is a microscopic picture is necessary to explain the origin of entropy. So this is this anti-de Sitter space. I already told you it has a negative cosmological constant. The metric indeed looks slightly different from the Sitter space. Anyway, this is the de Sitter space. Any-de Sitter space has a boundary, and the metric, it changes just the minus sign into a plus sign. But that changes a lot of properties because there's no horizon, there's a boundary, there's no temperature, and it's really like the anti-de Sitter space is like a ground state. It has no temperature, it has no entropy. It's really a unique vacuum state. And this is probably why string theorists like it. In de Sitter space, we have to go to an excited state with an entropy and a finite temperature. But in anti-de Sitter space, we know very well how to get gravity, and there's some way we can understand it from the boundary where we have a theory that is a conformal field theory, and then we start integrating out some of its degrees of freedom, and that actually corresponds to stepping into the bulk, because the radial direction that goes away from the boundary can be thought of as a renormalization group. It means scale. It means that I'm integrating out UV degrees of freedom and left with lower energy degrees of freedom. They are the ones that are closer to the center. And so I have a way of generating the space-time from the boundary, because the boundary theory really lives on the boundary. It doesn't know about the bulk. And so there is a microscopic theory and a macroscopic one where we have gravity emerging from the microscopic description. So this is an example of emergent gravity. It's also an example of the holographic principle, and we know a lot about what the microscopics look like. Here we don't have a question about what are the atoms that we have to look at, because we have this microscopic correspondence. So it's really a toy model, or actually a laboratory where we can learn about the rules of how to derive gravity. And it's that way that people discover that a very important role is played by entanglement entropy. So entanglement, which is a quantum mechanical property that connects different parts of space, actually in the quantum state. For those of you who are not familiar, I hope this is visible. There's a region of space where I separate the region inside and outside, which I call A and B, and I have a quantum state, which could be the vacuum state or some excited state, but I'm actually going to define what's called a density matrix by tracing over a part of the space. And you can either trace over the outside or the inside. Here I wrote down a density matrix where I trace over B, and then that means that the state no longer is a pure state, it's a mixed state, and it has an entropy that's given by a von Neumann formula for a quantum mechanical mixed state. And of course, if I trace over A or B, it doesn't really matter because the two entropies will be the same. And you can think about this as sort of measuring bell pairs across this surface. Now, in ADS space, we can do this on the boundary, and then it turns out that the entropy that you get, so this is the boundary, and here I have the region B, and there's a region A on the outside, and I can ask what is the entanglement entropy. It turns out that in this case it's exactly equal by the Bekenstein-Hawking formula, where the area here indicates the area of some surface that goes into the bulk, into the space-time, and it sort of ends on the boundary, precisely on the well, where I cut the surface into two, the boundary into two. And this is a connection between black hole entropy, where there's no black hole, because we write it really as Bekenstein-Hawking entropy, but in empty space. One way to think about this is that actually this forms a horizon for an accelerated observer. And then we also know now there is a temperature and an entropy associated to that. But this is purely entanglement entropy in this case. Well, this has all sort of led to a development in which one wants to understand gravity from quantum information. There's a whole well, consortium and a whole community of people working on this. It's sort of in the US they call it from qubit, where we really understand everything that's we are made of, and even the universe, from just quantum information as the most fundamental box from which to derive nature. So gravity in that context should be derived from some law of thermodynamics. It's called the first law of entanglement entropy, and I'll show in a minute how that goes a bit. But it also requires that the entropy is given by this area. And actually this is true in anti-de Sitter space, but we are eventually interested in de Sitter space. So what is the way to get gravity sort of look like? I mean, there's what I mentioned is this first law sort of goes like this. So here I have a region of space. I look at the density matrix again by integrating out the inside or the outside in this case. That density matrix can be written in a thermal form where there is an operator here which is like a Hamiltonian. That Hamiltonian turns out to be an expression in terms of the stress tensor and generates the time flow inside this domain. And then there is a first law, just like the first law of thermodynamics that I showed you, where you change the energy, then you change the entropy. In this case, it's very simple. The change of this entanglement entropy is precisely proportional to the change in the energy of this state. And actually, the reason is that this energy is sort of canonically normalized so that the temperature is always 1 over 2 pi. And so I get a direct relationship between the change in entropy and the change in energy. And if you think about the gravitational situation where I add mass or matter or anything into this volume, actually it turns out that the change in entropy in this energy, actually I should say, is related indeed to the change of the area. Actually it's a minus sign here. The area actually becomes smaller if you keep the volume fixed. And this is sort of like the first law of entanglement entropy. And it turns out that if you put this law in and you assume actually this equation, then you can derive this when you assume the area law holds. And this is a way to get to the Einstein's equations. Actually, it can be generalized also to other forms of gravity if you indeed replace the area by another appropriate quantity, as we heard in the first talk. So these ideas have been worked out by van Raamstonk and collaborators, and actually Jacobson actually followed up on this. And sort of they extended Jacobson's original art paper from 95 to derive gravity really from just quantum information. Just to say a few more words about this, one of the ideas is that entanglement indeed plays such an important role, is that it sort of keeps space together, because you can think about, and this is sort of from Scientific American popular paper, of article about these developments, where you can think about space-time really as having measured, that areas are measured by entanglement. That means if you reduce the entanglement between two regions, you really split the two regions into two parts. So entanglement is necessary to glue space together. And this is sort of where we're not talking just about emergent gravity, we're talking about emergent space-time. I already mentioned this word EPR is ER. That's sort of a similar way of thinking about it. In this case, you think about a black hole geometry. So if you take a black hole, an eternal black hole, actually its geometry looks like this, where there is a part of the space outside, the universe outside, and a part of its inside. If you cut it here at the time slice at t equals 0, the space looks like an Einstein-Rosen bridge. But the idea is that this bridge basically is representing the entanglement between the two regions. So the vacuum state, indeed, as Hawking calculated, looks like this, where you write states on the left and the right. So it's an entangled state. But now the idea is that the amount of entanglement is actually precisely equal to the area of this horizon, which is the size of the neck. So changing the area indeed changes the size of the neck, and then you can split it again. But it also makes it sort of glued together. And this is the idea of EPR is ER. And there are various people that have worked on this. Actually, it's an idea that Herman and I already had before these papers, at least the second paper appeared. And indeed, why does it play a role? Because it also is related to this information paradox about also the firewall discussions, because that basically goes about how much entanglement do we really have at the horizon. And it started a discussion even whether the horizon is a regular space of part of space-time. So horizons are really non-trivial parts of space-time. And also, therefore, in our cosmos, when I go back to de Sitter space, I have to ask questions. I mean, what does the horizon tell us? What does it tell about the space-time itself? And the reason that de Sitter space is different than anti-de Sitter space, the only reason is that I've added dark energy, a positive energy that is not present in de Sitter space, and that creates the horizon. So I'm going to claim and propose actually that de Sitter space indeed has also a horizon. It has a microscopic entropy, an entanglement entropy that you can think about as also measured by the area of the horizon. But in this case, the entanglement is not carried by anything in the bulk, because there's nothing here that can be entangled. I mean, in the case of ADS-CFT, it's actually parts of the boundary that are entangled with each other. Now there's no boundary. And so what is being entangled is actually the dark energy that's inside of here. And the amount of entanglement is exactly equal to this area. But now, where is the entropy really sitting? And this is where I go back to the beginning. I'm claiming that our universe indeed contains a lot of entropy associated to dark energy, and its quantity is precisely equal to the area of the horizon. So in the Sitter space, indeed, when I cut the space into two, when I take the global de Sitter space, actually, this is the picture that the northern and the southern hemisphere are actually the left and the right. So here like this. So there's an equator that actually is the horizon. And so we live sort of here. And then there's another side, and maybe those sides are entangled, but then the amount of entanglement should be equal to this area of the horizon. So that's the picture of the Sitter space, which is a positively curved space instead of negative. So it's very different from anti-de Sitter space. So now I return to my discussion about the dark universe and what is related, how that is related to emergent gravity. So I already told you that the total entropy must be equal to the area of the horizon of our universe. These are the temperatures, and this is actually the size of the universe if I think about it in terms of a static universe with a constant, Hubble constant. Then the de Sitter entropy and the temperature are due to the positive dark energy, and actually I propose now that indeed the dark energy carries the entropy. And therefore the entropy is not really equal to the area, I mean it's not sitting at the horizon area, but it's actually carried by everything that's in the bulk, because the dark energy is filling the entire universe. And so the total amount of entropy is equal to the area, but if you count it all up, actually it's given by the volume. And therefore if I ask how much entropy is contained in a region of space with a size r that's smaller than the de Sitter radius, it's a fraction of this entropy. Namely, it's a fraction that's proportional to the volume of that part of space. And so I write an expression that's giving me this result when r is equal to L, and then it grows like the volume, because this actually, when you multiply area with r, it actually grows like the volume. So this is a unique expression that gives you indeed the total entropy equal to this, and it actually is proportional to the volume. This has important consequences, namely when I add matter to the theory. I already told you that matter actually changes the entanglement, and actually indeed it reduces the amount of entanglement in the space. And this is where I'm going to actually now make a connection to what has been observed in galaxies. First, let me make another comment, namely that entropy indeed removes entropy from the space-time, actually can be computed. You can indeed use Einstein's equations for that initially. Namely, if I take the Sitter space, but I add matter to it, the geometry is slightly different than what I wrote before. You have to add a 2gm, actually there's a factor of 2 here, let me go back here. So this is the usual Schwarzschild geometry with when they add the 2. But this is then what's due to the dark energy, so this is the de Sitter part. But if you then ask where is the cosmological horizon, when I add the matter, it actually gets smaller. It gets displaced a little bit, and the area gets reduced precisely by this quantity, mc over h. So this was indeed the quantity already I wrote down before. It's the energy that you put in divided by the temperature, and that is the change of the area. So that is one part of information. The other part of information is indeed this entropy density that I wrote down. And actually we wrote a paper more recently about the microscopics, trying to explain where this volume law for the entropy comes from. And we called it, we had an argument that had to do with non-ADS holography. And this is in a paper with Manus and another of my students, San Leuven, and where indeed reproduced this volume law. So how many minutes do I still have? 10 minutes, okay. In that case, I will go a little fast through the next part. I want to actually explain a little bit more about this microscopic story. And this is going back to the ideas about what we know in string theory about the microscopic entropy. I told you that ordinary particles are not explaining the entropy. And so also the entropy in our universe should not be thought of as something that we can explain in terms of the particles that live in our universe. And this has to do with indeed how we think about how entropy appears in string theory, in particular also in black holes. So I'll show you quickly some slides that sort of go through this argument. If I think about entropy in terms of particles, I can think about, for instance, the particles that make a neutron star. But a neutron star, when I put too many particles together, undergoes gravitational collapse. And you may wonder what really happens to the particles when this happens. I mean, there was a certain amount of phase space occupied by them, and suddenly I get a black hole that has much more entropy. So what happens really inside? String theory gives sort of an answer, and actually there's a clue here. I mean, there is statistics involved in describing these particles, and statistics has to do with exchanging two particles, 1 and 2. And this is a discrete operation. Namely, you exchange these two particles. But you can do something continuous, and this is actually what happens in string theory. We can rotate particles using sort of unitary transformations. We can rotate particle 1 into a linear combination of two particles, or maybe even more particles. And that actually changes the number of degrees of freedom drastically. The only thing that we have to give up then is actually the notion of having a unique position for each particle. Because if I have one particle becoming two particles, then suddenly we have to wonder what the positions mean. And positions indeed can have matrix elements then between two particles. And then actually it turns out that the positions become matrices. So if I have two particles, the coordinates of my space-time becomes a 2 by 2 matrix. And this has to do indeed even with strings sort of connecting these particles. And this you can generalize to larger number of particles. If I have n particles, you get actually an n by n matrix where the diagonal elements are really the positions of the particles, but the off-diagonal modes can become important as well. Actually, normally we don't see them, and this is where we are in the phase where we see normal particles. But there is, when we put the particles too close together, these off-diagonal coordinates become important. And this is exactly what happens in, I should have written this differently. Yeah, this is the one. So this is actually the situation when we have still the particles. The particles are described by their coordinates, and these off-diagonal modes are not excited. But when the collapse happens, then suddenly all the particles get closer together, and we get much more entropy in this state. And this is what we call actually the Higgs branch of the theory. And suddenly we get indeed these open strings connecting them. And this is the phase that this carries all the entropy. That phase also occurs in our universe, but it's a phase of strings that are really of the size of the Hubble radius. And they carry the entropy. So this is the two phases of string theory. And already getting ahead of myself, I mean, this is indeed the particle picture. This is the picture that carries all the entropy. And so our universe is sort of in a mixture of those, because we have some parts in terms of particles that we know how to describe, but we also have something that's really connecting all of space and has an entropy associated to it. And so what is now the explanation of what really happens in these galaxies? I already told you that the observations tell us that this acceleration, when it drops below this number, actually tells us that that's where dark matter effects become important. This is where rotation curve starts flattening. This is actually rewritten in terms of a quantity which I call, this is actually the Bekenstein entropy that I introduced in the beginning. And this is the entropy that's actually contained in the dark energy. So the picture is like this. This is the entropy that's carried or actually taken away by matter inside a certain region. So I take a certain region of size r, then the entropy associated to this mass is given by the Bekenstein formula. The entropy associated with the dark energy is by this volume law that I already indicated. And it's precisely when this drops below that we start seeing the deviations. And this is where the dark energy starts taking an effect and actually pushes back. And this is what you can calculate. And I'll show you just some plots at the end of this talk. I mean, there's some way that you can calculate when the amount of matter that you put in, actually it reduces the amount of dark energy. It actually reduces the amount of entanglement. It's sort of like removing part of a medium. And there's an elastic response. These are pictures from the paper I wrote on this. And the entropy actually changes the nature of gravity because actually there's a volume law that takes over. And what is the consequence is a relation actually between how much matter you put in and the acceleration that deviates from Newtonian physics. This is called the radial acceleration relation. it's a relation indeed between the observed acceleration and the one that you would have from just baryons. If you put them together, actually you measure them, you can actually see that there's a correlation. This is this radial acceleration relation due to these authors. And it's one way in which sort of there's a possible explanation, namely that indeed the amount of baryons somehow seem to know how much dark matter is needed. So this is what this is indicated in this picture. So this is the amount of baryons, this is the observed acceleration, and you sort of see this relation. And actually in this regime, so if it would be just Newtonian gravity, we would be on this line. So the deviation is this difference. But there's also a linear relation, or a linear relation between the logarithms, which means there's a scaling relation, which for large r, which means in this region, actually looks like this. So the observed acceleration squared is equal to the baryonic one times this number. This is actually the basis for the Mond phenomenology due to Milgram, and it's something that indeed can be verified in many galaxies. But the explanation I gave here is actually this, is that there's a galaxy that's sort of surrounded by dark energy, some information density, which I hope you can see, but there's bits around here, and that actually creates the additional effect. So now I have 2-3 minutes. So I'll indeed, I'll just give you the punchlines. I mean, there's a calculation I can do, not in 2 minutes, but I can show you sort of the result. But just to give you an intuition for where it comes from, I mean, first of all, the dynamics of this additional gravitation of the dark energy is not at the scale that we can observe. It's a very slow dynamics, the temperature is very low, and therefore it's not something that you can write down simple in some simple field equations. And this has to do also with the fact that our observations of gravity are really at a short time scale. We can understand gravity very well when two black holes collide or something like that. We know what the response is. It's like phonons. I mean, that analogy was made already. I mean, where you hit something and you know these things are going. I mean, there's other phenomena that can happen at much longer time scales. And maybe I should show that. Well, I'll show that actually in the question session or later, the 4 questions. Indeed, sort of what the idea is that indeed the universe, what we have observed is only a very tiny fraction. And we have not seen all the dynamics, and there's dynamics hidden in a dark energy. And the reason is that there's something going on in the way that space-time is made that is associated with this entropy that's there. And entropy generally can sometimes be hard to detect. When I look at a state of a material like quartz, it has a unique ground state. When I take glass, it has sort of very similar properties as quartz, but it has a lot of entropy in there and a very slow dynamics that's very hard to detect. And many properties, like when you shatter it or do some things to it, are actually similar to what quartz is, but the entropy makes a very big difference. And I claim the same actually is true in space-time. And so what I wanted to show actually, and I sort of have not enough time for that, is actually that indeed from these arguments I can actually calculate what is going on or what is changing in the nature of gravity when this relation is happened. So this is actually a measure for the amount of entropy that is taken away. And actually I'm going to need to show you a formula that is for this analogous to the relation that this radial acceleration relation. This is the relation I can derive from this microscopic picture of dark energy, where I've integrated the observed acceleration squared. And so it's the same relation actually between the acceleration of the observed one and the baryonic one, except that I've integrated it. But if you differentiate this again with respect to the radius, so this is an integral over a certain region up to, say, radius r. If I differentiate this with respect to r, I get back a relationship between the acceleration and the mass, which you can rewrite as a relationship between these accelerations and the Hubble parameter. So this formula actually can be tested, and Margot will probably say more about this in her presentation. But it can also be derived from the arguments, and I'll only sketch this in the next slides. Actually, I have to skip this. There's some actually derivation based on elasticity that I found actually in a paper on polymer melt. This relationship is a relationship for the elastic energy inside a certain volume. It's proportional to the amount of sort of polymers that have been removed. Actually, this picture I already showed you before. Actually, it's a very similar calculation. Matter actually removes a certain volume, and you can calculate this energy. And there is a number of correspondences you can make between elasticity and gravity that I've worked out, which precisely maps this relation onto the observed relation. Namely, the integral of this elastic energy becomes the integral of the gravitational energy, which is because there's some direct relationship between the acceleration and the strain tensor, which all involves constants that are precisely in acceleration scale. And then you can map these relations onto each other. And so this is a derivation I've presented, but indeed it's based on the idea that dark energy plays a fundamental role and has an entropy associated to it and its own dynamics, and starts playing a role exactly at the scale that we are observing it. Thank you. I'll stop there.
Thank you very much. Is there any question?
Yes, I have a question.
I hear you, but I don't see you.
There we are.
Yeah.
Steve
Okay.
Anastasi. I'll be presenting tomorrow. Professor, if I could just ask, I might have misheard you. You said the baryons, I know you're talking colloquially, but the baryons know how much, did you say dark matter or dark energy is needed?
So dark matter for me is a way of filling in a gap in our observation, in our understanding of the observations.
So you're just referring to, seems to know everything else what's needed. Okay, I understand. So my next question simply...
No, that's not what I said.
I apologize. I'll listen to you talk. I apologize.
In this part of the observations, they seem to be correlated to what we observe in the effects due to dark matter. That's what I was alluding to. That doesn't mean that they know everything, which is sort of an extrapolation of my comment that I'm not going to make.
Thank you very much. The other thing, I was just wondering, I noticed in the equation you had there, MB was for baryon mass.
Yes.